recently joined UFT. I'm also in chemistry, and I have also a cross appointment with physics just for the fun of it. And I also have links with the Vector Institute. So one of the reasons I really wanted to join UFT was that there's a dedicated effort going on, which I think is extremely timely. It's super exciting. It's happening now, and one of the top places for where it's happening is Toronto. So it happens in these departments I just mentioned, and there's also, of course, the computer science department, but the faculty of engineering and the faculty of arts and sciences, I think, hosting really amazing efforts here. So I'm really thrilled about this, and I'm already enjoying myself a lot since I've come over. And I'm showing this slide just to give you a backdrop on what is going on, if you're not aware of this. So this robot revolution that's happening, I think you can all agree, right? So if even the Wall Street Journal is telling this, I think then it's safe to say that this might also be of relevance to us. And there's this question surrounding the acceleration consortium, which was founded only recently in Toronto. There's this effort where we would like to accelerate the discovery, the design, the path to market of novel materials, and also of processing of materials. Now, you might not know, but conventionally, bringing a new material to market is, on average, ballpark wise, something like 10 years. And for various reasons, we would really like to accelerate this much more, right? So there is a glimpse of hope that this is possible, and that hope is sort of founded in these keywords shown here. So of course, the robots, right? This idea. Here you see robots assembling cars, but you can imagine such robots performing experiments. There are various groups already on the planet, and multiple of them in Canada, that are doing this. They're experimenting with robots, and they try to streamline the experiments. Now, every robot requires a trained scientist who advises the robot, who trains the robot, or makes sure that the experiments make sense, and so on. So I don't see these robots as something that will displace the scientists, but rather it will increase the productivity and the efficiency of the way we do the science. Right? It's sort of a lab assistant, really, that could dramatically improve and accelerate our research. Now, I was in Vienna in the faculty of physics as a professor, and I have a strong belief that at the end of the day, we want to exploit the power and the generality and universality of the laws of physics when developing new materials. And so I think we should use physics also together with computer simulation. You might have heard of Moore's law. This is, of course, an amazing development, and just over the last couple of years, we have seen a tremendous improvement in compute power. And so simple devices such as a phone would have been considered a supercomputer just a decade or two ago. And now you have it in your pocket, and these machines are really powerful. And so we can make very good use of them. Then we also have increasingly more data at our disposition. And what's shown below here are the statistical learning algorithms that are used to create artificial intelligence methods that have been shown to really also be helpful. And they could not exist without the data. So without data, there is no AI. But given that we have increasingly more data due to increased digitalization, due to robots, we have now the possibility to also make use of statistical learning. So I think all these pieces, they come together, and this makes me hopeful that we can do something which I like to call quantum machine learning. So we want to use all these ingredients for the challenge of understanding and navigating and purposefully designing and discovering new molecular materials, new solid materials, new solvents, right? So any aggregation state is something we'd be interested in. And thanks to the laws of physics, again, them being so fundamental, we think we can do this also for all aggregation states, for all process variables. Now, at least in principle. So what you see here is an animation of the 1,000 smallest molecular fragments from which you can build organic molecules. It looks like a lot, but actually it's a surprisingly small number of fragments. They can already be used to construct machine learning models that would be predictive for a lot of organic chemistry, right? And so requiring only 1,000 building blocks for covering all of organic chemistry is something that would be quite a good deal. Now we are working our ways towards establishing similar fragments also for materials and solids and liquids, and tackling all sorts of properties. So I'll tell you about that in today's talk. But I'd like to start out by giving you sort of a conceptual overview how I think we can view recent developments in our field. So at large, let's say the atomistic simulation community. So of course, science would not exist with experiment. So in some sense, the experimental pillar is the most fundamental to science. And then to build a theory about what we observe is something that has been going on ever since the Greeks, or also in other cultures, right? There were scientists who contributed. So among others, names to remember Euclides, Pythagoras, or Archimedes. Then later on in the Enlightenment period, right? Here you have Newton, Dalton, and Darwin. And then the more modern sciences are shown, illustrated by these fellows down here. This is Max Planck, this is Albert Einstein, and this is Ludwig Boltzmann. I made an effort for these last ones to find pictures that portray them when they were active researchers developing their theories, right? And they look a little bit crazy and unassuming, right? And so maybe that invites you to also not get distracted by the appearances. So the big thing that then happened in the in the 20th century really was the establishment of computer simulation, right? So the computer, to me, is one of the most amazing achievements of human mankind. It's hard to, of course, to select names or people who represent this. So this is a picture of John von Neumann, and this is Konrad Zuse. So I grew up in Germany. I had to put Konrad Zuse since he's a German computer scientist. But of course, there are many others. So these are just selections, right? I don't claim that they are complete. Now, I think what's been happening then at the beginning of this century, 21st century, is really that a fourth pillar was established, and I call this machine learning now here. Also there, success always has many parents, right? But I'm putting down two famous names, Vapnik and Chervonenkis, who contributed a lot to the theoretical foundation of statistical learning. And of course, there are many others who contributed very much. So the way I see this is that all these pillars, they can benefit from stimulating each other, and in some sense we'd like to make use of all of them, right? Now in my research group, we do everything but the experiment. So we focus on this theory, the effort you have to undergo in order to perform experiments, I think is so large. I'm not against this, right? Obviously, but we feel we don't have the resources to really do this, and so we rather collaborate with experimentalists, or we take experimental data from the literature, and that has turned out to work quite well. Now, coming to what we are interested in, really, in terms of this chemical compound space, I think one should always start with the alphabet. For matter, of course, that is really at the atomistic level, at least, is the periodic table of the elements. So just 3 years ago, we had a big birthday celebration, 150 years since Mendeleev proposed this, and it even got a contribution in the New Yorker, which is a journal. I don't know if you read this regularly, but it's quite rare that a natural science topic makes it into the New Yorker. So I was delighted to see this. So the periodic table, as we see it here, right, constitutes in some sense the alphabet from which you could make all sort of materials. Now you have to select, of course, a certain number of these letters, and you have to arrange them somehow in space. But you could view materials as words in this kind of language of matter. And so it's not surprising that maybe that natural language processes, recently developed machine learning models in the field, have been applied to such problems quite successfully, right? So to view materials as the information stored in materials, to recast them in the same way you would recast a language problem, a text, an essay, that seems to be not entirely inappropriate. But I think there are some strong differences, of course, and so I'd like to tell you a little bit more about my view here. So for one thing is that our alphabet is sort of the sequence of the letters is in some sense arbitrary. And so that also, of course, applies to the ABC. And so here you see different representations of the periodic table, with the exception of the lower right-hand bottom figure here. I think these three representations, they are valid representations. You could reorder your elements in this way just as well, and you also will recognize some periodicity, right? And so this begets the question: what is the best way in ordering the alphabet, right, the periodic table? So I think these questions are so fundamental, and I also think there's such strong similarity to the alphabet that I'm really surprised that, for instance, in our educational system, students learn about the periodic table rather late in the curriculum. So I have little kids who go to elementary school now, and so the idea to teach them already about the periodic table at school at that age, contrary to the traditional alphabet, seems to be really unusual, and I don't really understand why. I think kids should know about the alphabet of nature just as well as the alphabet of languages. But these are more educational remarks. Pushing this further, there's another representation of that same alphabet, and you see that there's some beauty in it, right? And I enjoy thinking about this and talking to people about this. And but there's actually real applications of this as well, right? It's not just an aesthetic or math kind of mind play, but there's more to it. You should know this already just by thinking of the story of Mendeleev, how he found out about it, right? So given properties of elements already known to him, he would predict the property of the missing elements, right? And so that is, in a nutshell, that's already machine learning, right? That's what machine learning would do. So he was doing machine learning in the 19th century. Now, more modern approach was put forth by David Pettifor, a material scientist in Oxford, who in the 80s, he proposed this Mendeleev numbering scheme where he would go through the periodic table and he would connect elements in a different way. So here you see it going down just a group. That's sort of intuitive, right? And here he goes up again. But here you see some weird connections, right? So he's changing the order of the elements, right? He's rearranging the order in that periodic table. Now, why would he do that? You see a reason here on the left. So if you follow the order he proposes, right, for these elements here, you see that the formation enthalpy of carbides or nitrides just becomes linear, right? Now the formation energy is it's an incredibly complex property. If we wanted to calculate the formation energy from scratch, from quantum mechanics, we'd have to solve a really, really difficult problem, right? You'd basically have to solve the problem of atoms bonding to each other, being glued together by the electrons. And electrons are quantum objects, so you need to solve the quantum equations of that problem. And we can only do this with approximations, very severe approximations and very big computers to get something reasonable. And what Pettifor is telling us here is, well, you don't need to do all of that. You can simply rearrange things. And then if you have an experimental number for just two of these, right, then you do a linear fit, and then you can infer the formation energy for anything in between by simply inverting this linear equation. Um, so that's really amazing, right? Because it tells you that materials properties, right, that where we know they originate in very complicated physics, as you navigate chemical compound space, a lot of the differences level out in something in a low dimensional projection, something very complicated, just becomes linear. So this was the 80s. You might wonder, is this also outdated? Presumably, most of the younger students here were not even born then. So this is a paper by Hardy Gross and Miguel Marquez, two leading scientists, theoretical physicists, working on electronic structure problems. And it's from 2016, where they revisited the Petitfort scale for data mining. Right? So you see, this is not, I'm just showing this so you see this is ongoing research, right? But of course, chemical compound space often contains more than just two elements, right? So these are basically just binaries, right, with carbides or nitrides. So we'd like to have something else, and so then you will have more dimensions, and so we need to go beyond that, right? And so I want to revisit again the theory and the simulation part of these things. So this is now a little overview on how the field looks like if you consider materials compound space using just, in quotation marks, physics and computer simulation. Now, this is completely justified, as also stated here by this famous quote by Paul Dirac, one of the founding fathers of quantum mechanics, that the fundamental laws necessary for the mathematical treatment of a large part of physics, he was talking about physical chemistry, materials physics, solid state physics, and the whole of chemistry, which is quite a statement, are thus completely known, and the difficulty lies only, I would put that in quotation marks nowadays, in the fact that application of these laws leads to equations that are too complex to be solved. Now, Dirac, this is the 30s or so, there were no computers yet, right? And so this third pillar of numerical simulation was crucial to actually demonstrate and back up and confirm this statement. And so at the end of the 20th century or so, you could make figures just like this one here. So what are we seeing here? It's the error of your prediction, of your calculation, right? Where you deviate, where you measure the deviation of your calculated prediction from the experiment, right? Of course, the experiment is the arbiter, which is why experiments are so important, because they, of course, as you know, have an uncertainty. And this experimental uncertainty is sort of the window where you would like your computational prediction to get into, right? Once you're in the experimental uncertainty window, you can no longer distinguish the theoretical prediction from the experiment. In other words, then at that point, your prediction is just as good as the experiment, right? Now, you could argue, why would you need that? Why don't we just experiment? The answer is rather simple if you think about it. For one, there are scenarios where you simply cannot perform an experiment. For instance, how do you measure the chemical composition of the Earth's core? Right? Nobody can dig down there. I mean, it's just impossible, right? How would you measure its temperature, right? Or some faraway planet? How do you measure its properties? Or at the atomistic detail in some biological organism? How can you measure something, let's say the reaction rate of an enzyme, right? So there are many experiments which we can sort of conceive theoretically, but which will be close to, if not completely impossible, under any circumstances to actually realize in reality. So that is sort of a practical argument why we really want to have theory and predictions. But there's also another argument where fundamentally you could say we would like to understand what is going on in nature, and if your theoretical prediction corresponds to the experiment, then you could argue that you have understood the problem, right? And so this is also an important, more philosophical argument in that direction. And lastly, let me add a third argument why we would like to do theory and predictions. It is an argument also of efficiency, right? So typically your theoretical prediction is less costly and more efficient than the experiment. And that means if it's at the level of the experiment, you can augment your experiments by theory, and you can make it 10 times, 100 times larger, and learn from that data you accumulate more about nature. So you accelerate the entire scientific process. All right, so what are we seeing here? We see the error typically made by force fields. So force fields are simple-minded presentations of materials where you assume simple relationships between atoms, energetic relationships between atoms in terms of bonds, in terms of angles, in terms of dihedrals. These force fields are typically very crude if you think about the details. For example, a dihedral degree of freedom will involve only 4 atoms, right? So it's a 4-body contribution. Now, typically they are only considered for atoms that are bonded to each other, meaning we neglect all 4-body contributions of non-bonded pairs of atoms, which is very crude. The same happens to 3-body effects. Angular distortions are also typically only considered between bonded atoms. And so if one of the 3 atoms is non-bonded, we neglect within the typical force field implementations, we neglect that 3-body contribution. Now, these contributions can contribute on the order of many kcal per mole, and so it's not surprising that your error is that large. Now, SE stands for semi-empirical quantum chemistry. There are certain integrals in your quantum mechanics of electrons in atoms, in atomic clusters. There are certain integrals of these electronic wave functions that are more costly than others. And if we neglect those, the calculations become much faster, of course, but unfortunately, these integrals are also important. So you do get sizable error here. If you don't neglect any integrals, you can still make approximations where you have something like a mean field of the electrons. So not every electron talks to each other, but rather an electron talks to the average of all other electrons. And that's what Hartree-Fock implements, and this gives you already a decent energy, actually. So Hartree-Fock is sort of the most useful approximation in quantum calculations in terms of getting your error to a level where you get something close to be useful in order to predict experiments. So 15 kcal per mole is an error which you should compare. Let's say the energy stored in a covalent bond is on the order of 100 kcal per mole, typically a little bit more. If it's a double bond, even more. So think about bond energies of 100 kcal per mole just for one bond. Of course, in larger systems, you have many bonds. So then getting a total error like this for your average molecule is really not that bad. For solids and extended systems, you would typically divide this error per atom, right? Since the number of bonds depends on your number of atoms, of course. Now, as you include an explicit correlation between the electrons, as done in this perturbation method, you can still dramatically reduce this error. This is Möller-Plesset second order perturbation theory. It's a beautiful accomplishment in the history of theoretical quantum chemistry. Unfortunately, the perturbation series, if you think of it like a Taylor series expansion, this perturbation series in your electronic degrees of freedom was shown to not converge. So you cannot simply improve on MP2 by adding higher orders. Rather, what you need is to go beyond perturbation and to do the full correlation, everybody talking to everybody. And that's something you can do with quantum Monte Carlo, or you can approximate it very well with a couple cluster single double perturbative triples. These are excitations in theoretical orbitals. And it turns out if you do the full excitations for up to double excitations, and then you add a perturbative triplet excitation, then you get to 1 kcal per mole. And this is an important number, 1 kcal per mole. We call this the chemical accuracy. Chemical accuracy, because this is the typical historical sort of experimental uncertainty you have or you encounter when you do a combustion, thermodynamic combustion experiment in a calorimetric device, right? So if I want to measure your heats of formation in a calorimeter, you would struggle to go in your experiments to get an uncertainty less than 1 kcal per mole. So of course, if you do spectroscopy, you have a smaller error. We call this the spectroscopic accuracy. But for many chemical reactions, really, this is what constitutes a useful goal. Now, you see the error coming down, but as you want to become more and more predictive, I gave you just 3 arguments why you would like to be more predictive. You see that there's no free lunch and you have to pay dearly in terms of compute time. Now, compute time is directly proportional to money. And so if you're from a wealthy country, you can afford to be more accurate than people who happen to live in a poorer country, right? So this is sort of a Pareto front, negotiating error versus available compute cost. And the fact that we have these computers, that this cost is relatively low if you compare to the past. This is, of course, thanks to Moore's law, right? So we can build computers that fill up entire rooms, and they can help us with solving the relevant equations as implemented by the people who program the software that does basically it tries to solve Schrödinger's equation, which you see written here is the Hamiltonian, depending on nuclear charges and coordinates, and it's the electronic wave function. Right? Now, this is sort of the picture, and since this is such an important trade-off, this the Pareto front of the best combination given some budget. This is the best error you can have. Of course, you can choose some other method where you burn the same budget for, but if it's less efficient, right, and worse, then you will have a higher error. So your best method should be on this line. And conversely, if you wish to have a certain error, which you find acceptable, then this will tell you how big the computer has to be, which you need to buy to solve that problem. Now, in the towards the end of the 20th century, there were important contributions made towards shifting down the spheroidal front, right? So the mean field theory, called density functional theory, is immensely popular in the materials and chemistry communities. And one of the founders, Walter Kohn, shared the Nobel Prize together with John Opel, who developed also these codes and methods for these more correlated methods. So in 1998, they both shared the Nobel Prize. This is John Opel and this is the Swedish king. And the merit is, of course, that they managed to pull the Pareto front down. So for the same cost, where previously you would only get this error, you can now get a much lower error using density functional theory, or using a tight binding density functional theory, which is also a very decent semi-empirical method. So what we need to do in order to sample chemical compound space now is to work on this Pareto front. And since there's so many possible materials and compounds, right? Just think of the possible words you can make from the alphabet, right? The situation is the same. It's a combinatorial explosion for possible materials you could make from the periodic table, right? Now, just as with words, right? Not all combinations of elements are necessary to be considered, right? Some will be unstable or uninteresting. So the same thing for words, right? Not any arbitrary combination of letters will form a word, but you have still an immense number of possibilities. And so this question, how can we accelerate this? How can we push down further that for each and every individual material, we can avoid this Pareto front? This is really what is behind the efforts in my lab. And so the way we see this is that we pursue two directions here. One is based on perturbation theory, and one is based on correlation, right? So if you wish, one is physics, this is the physics-based one, and this is the AI-based one. So this cartoon here is supposed to illustrate this. Imagine you solve Schrödinger's equation for the black dot here. You could now do perturbation, a Taylor-based approach, if you have the derivatives to predict all these other open symbol cases, right? And you can do this for the surface, some property surface of just one material, or also towards another material, right? And the reason we can do this is that the nuclear charges and the composition in our models, just as I showed you before for the periodic tables, they are arbitrarily. We can solve Schrödinger's equation for any arrangement of these elements and coordinates. And so the quantum mechanics of the Hilbert space, in which all your electrons live, is more general than what we actually observe in nature, where things are just limited to the systems with measurable lifetime and with nuclear charges corresponding to integer numbers. In theory, the quantum mechanics is more general, and we can also include non-integer nuclear charges, and we can consider geometries which would have negligible lifetime in reality, right? And we can do quantum mechanics on those. So maybe an analogy for this sort of crazy theory where you move, and that's why we use alchemy. We consider situations which lack correspondence to reality. Maybe the best analogy to this, to convince you that this is not craziness, is the ideal gas law, right? We all know this is not a real state function, yet it proves to be quite useful for developing not only our frameworks in thermodynamics, but we can also even use it to create thermodynamic cycles which facilitate calculations and predictions of experiments, right? So in that vein, we can use physics and perturbation theory, more particular, to deal with changes of the energy, let's say, as we go from one initial Hamiltonian, the Hamiltonian representing your system, towards a final Hamiltonian by tuning an interpolation parameter lambda here. So lambda would go from 0 to 1. You can continuously tune it, and one Hamiltonian will be morphed into the other by changing lambda continuously from 0 to 1. Now, it turns out in quantum mechanics, there's a famous theorem called the Hellman-Feynman theorem, which tells you that the first order derivative of your energy with respect to that interpolation parameter is the same as the expectation value of the derivative of the Hamiltonian. Now, this is not necessarily an obvious equality here. Once you learn about the Hermitian properties of the Hamiltonian, you can easily derive it. The proof only takes a couple of lines, but this is something quite remarkable, and it gives a lot of food for thought, right? That your derivative of the observable should be the expectation value of the derivative of your operator, right? So this operator and observable duality, this is something which has interested people for a long time. And it's something very fundamental, which we are also exploiting then, and I'll come to that later on in the machine learning, because we consider our Hamiltonian, the operator, as the input to the quantum mechanical problem, and the observable, just as the energy, as the output to that problem, right? So nobody in his right mind would confuse input with output, right? And so this offers this view on quantum mechanics as something where operators are input and observers are output, has proven very helpful in our work as well, when we move to very modern things such as artificial intelligence. Now, if you consider this derivative here, you see that we can write it down, for instance, for the nuclei. I show this here, right? So you derive the Hamiltonian with respect to nuclear position, or you derive the Hamiltonian with respect to nuclear charge. And then this is the force on your atom I in the x direction, right? You get the derivative of the energy with respect to that displacement. And here you would get an alchemical force, the change of the energy as you modify the nuclear charge, right? As you modify the nuclear charge, you go to the left or the right in the periodic table. So for example, you would change carbon to nitrogen or boron, and we can calculate that derivative with the Hellman-Feynman theorem. Now, I can, of course, look at the Hamiltonian. Where are the nuclear charges? Where are the coordinates? And you will see they are only in the external potential, which is a multiplicative term. And so you can simply write this observable, this expectation value here, as the integral over the density multiplied with the derivatives of the external potentials. And if you then consider the higher order derivatives, you can see that in a Taylor expansion-based view, if you insert this for the derivatives of the energy, you only get derivatives in the electron density. Right? So here you also see why density functional theory plays such a fundamental role in the atomistic simulation sciences. So the other picture coming from AI is that you assume that you know all the open symbols, okay? And you do not know the black symbols. Now, what is the statistically most likely value the black points should have in terms of their output function, right? Given that you know about all the open symbols, right? And this precise question has a name. It's called supervised learning. It's a supervised learning problem, and supervised learning tells you that given sufficient examples of input and output, where we know and from physics that we can perform this map by solving our eigenvalue equation, then we can train a model on this, and for a new out of sample input, we can predict the energy as an output. Now, so these two coins, you could view them as AI versus physics. This is just a dramatic illustration to wake up some of you who maybe have fallen asleep by now. I don't think it's so confrontational, but rather a cooperative way they interact. But it's always good to have drama, I suppose.
Yeah.
Hello? Yes?
Oh, sorry.
Okay. So I'm showing here now a little illustration of these alchemical changes in their perturbation. And maybe the simplest non-trivial example is if you count the N2 molecule, and you see here its electronic energy as a function of the interatomic distance. And for N, this would be the red line, the ridge on this curve. And if you change the nuclear charge of N2, which is 7 and 7, to 6 and 8, you would have CO, or 8 and 6, and so you have OC, right? And so due to rotational symmetry, you see that this ridge must be perfectly symmetric. And so what you also see is that this is very smooth, right? The surface. So chemical space, and this is contrary to how we grew up by learning that every material is separate and we have to study each and every one of them as if they were different species. Actually, in some communities, different materials are actually called species, right? And from the quantum mechanics point of view, that's not true. They are all related by each other. They're all part of the same Hilbert space. And you see that I can show you that this holds for N2. This is the electron density. And these are now perturbed electron densities of first, second, third, and fourth order. And as I mentioned before, they would enter a Taylor expansion. I can construct the electron density, for example, of CO as well as BF. So basically going down here, down this path, right? I can predict these electron densities just by doing the Taylor expansion around N2. Now N2 is sort of boring because it's just two atoms and you can rotationally invert it. But we recently discovered a new symmetry in chemical compound space, which becomes obvious if you have at least 4 atoms. And I'd like to briefly tell you about it. So this was published in Science Advances, and you should consider for this the benzene molecule shown here. And I can perturb this benzene molecule towards something like this alchemically. So the BNNB doped variant, right? So this would be the perturbing potential here. And this is now showing you there would be NN atoms and BB atoms here, right? Now my first order perturbation in the electron density from benzene leading towards this molecule looks like shown here. And it turns out that I can also consider the NBBN doped case. Now what you see is that the perturbation simply is anti-symmetric, right? It has opposite signs. So it's an anti-symmetry relationship. And what you then find is that the 2 first order derivatives in the energy, they happen to have opposite signs. And so if you take the difference between these 2 molecules, then this term cancels. And so they are near degenerate in their energy. The higher order terms here, unfortunately, the second order term does not cancel, but then always the odd order term cancels. So we have an approximate degeneracy. And so due to this anti-symmetry relation, this alchemical anti-symmetry relation, we call this an alchemical chirality, because you cannot superimpose these 2 molecules and any other 3D symmetry operation. So this alchemical chirality relation is something we recently figured out thanks to the Hellman-Feynman theorem and thanks to nuclear charges being flexible. There are important constraints on the chemical bonds that arise due to that. So we know that the chemical bonds in this isomer, they should more or less sum up to this chemical bonds in this isomer. And from this, we can solve for a new chemical bond expressed in the basis of other chemical bonds. And so this tells you how we can navigate chemical space in a more efficient way by exploiting such relationships that exist in this space. I need to speed up a little bit, but I can show you here another example. It's of course not restricted to benzene or anything. These are now in a diamond lattice. You see, I can also change my carbon atoms to NNNB or to NBBN. And I know these two fragments, they will have the same, approximately the same energy contribution. I'd like to tell you now how machine learning changes the picture of all of that. And so again, this AI versus physics picture. So 2011, I organized a program at the Institute of Pure and Applied Mathematics at UCLA on the topic of navigating chemical compound space. And the people in the institute, they invited a professor of machine learning from Technical University of Berlin, Klaus Müller, to participate in the program. And so I confronted them with this problem of chemical compound space and how could we infer solutions to it. And he proposed we use this kernel-rich regression method. So this is a very one of the simplest ways of doing machine learning, and it's very well established and very well understood. So it simply expands the property of a new material as a sum over training instances, where you measure the distance to your training material with this K function. This function basically measures the distance between 0 and 1, right? So it's a value between 0 and 1. If it's 1, it's the same. If it's 0, it's very distant from each other. And each training instance gets a weight as well. So this weight carries the unit of your property, right? So it looks a little bit like this. You have points. Each material is a point. And this point, you connect all these points in a kernel matrix. It's this K matrix. And so if you have this for your training material, you can invert this matrix, multiply it with the training reference properties, and that gives you the coefficients which you then use in your expansion when you predict a new material. So it's super simple. If you think about it, you can probably program this in an afternoon. And if somebody gives you the training data and the materials, then you have a working machine learning model. One technical question was, how do we represent the material in this expression? So to actually program this, you need to put a definition here. And the definition I proposed was this Coulomb matrix. It's a simple atom by atom matrix. This is how we got started. And so with this simple expression, and my collaborators, Alex Tkachenko and Matthias Rupp, he's a professor of physics in Luxembourg, and Matthias Rupp is a professor now in Constance. We were able to train a machine learning model on quantum energies. And of course, now you don't have to solve the quantum problem anymore for every material, but rather you provide this as an upfront cost. So your training set size represents the cost. Again, there's no free lunch, but once you've trained this, your trained model now can make a prediction at the level to which you train for out of sample systems in mere milliseconds, right? So there's actually proof that this error must decay on a log-log scale linearly with the logarithm of the training set. So we showed this in the second paper in 2013 also for neural nets, that you can train a machine learning model like this. So with this, I'd like to conclude basically that we have these 4 pillars. We have in the machine learning world these learning curves, which are very helpful. So I have a course developed on this. I hope to offer this course sometime soon and at UFT as well. How we can control the offset and the slope of these learning curves, since they really determine the cost of making use of AI. There's some reviews here or perspectives I wrote in the past, and with this I'd like to come to an end today. I had some more examples I could have told you about, but I've taken more time in the introduction, so I'm not going to tell you about this. But of course, you will find these topics covered in the literature which we've published recently. If you're interested in this, please feel free to look those up. I have to show you the people who did all the hefting behind this. There are multiple people.
I'm not sure if I'm frozen or if Anatole has frozen.
And it's changed the.
Okay, can you hear me, Anatole?
Yes.
Oh, I think we lost you for 10 seconds there, but
oh, I'm sorry.
We're back now.
What I wanted to say is I still have to thank the people who did the work. These are the students who've been in my lab. I've shown you a lot of the alchemy was done with Guido von Rudolph, and the more recent papers I didn't have time to take about were done by the People's Circle here. But so with this, I'd like to thank you all for your attention, and I'm happy to answer any questions.